All right, so we're going to start with 20 here. Human-powered aircraft. Same power output about that. How much energy did the pilot expend during the flight? How many candy bars would that be? All right. So we got to add our y for this one. Notice is a text y. So change that to 20. Right. So I'm going to start off right away because they talk about human power, and they talk about the power output. But then the question is about energy, right? So I'm looking for that relationship between power and energy, and power is the rate that something like the oh, that's completely spelled right, wrong. Like the rider produces energy. The more power, the more energy. I cannot type this morning. Energy in the same amount of time. The rider must get this energy from their food, since we cannot make our own energy from sunlight. Who says we don't talk about biology? Right? So the energy's got to come from somewhere, and power is the rate that something produces energy. So, any questions there on the how? I think that would cover it. Brings it in. I probably should have used the word pilot, but it was stuck in my brain. All right, let's go down here. We know we're looking for the relationship with power and energy. So I'll grab my snipping tool, and I'm going to grab this whole host of equations, which are about power and energy. And then we'll just stick them in here, and we'll see which ones we use. All right. And let's see, what do we know? We know the power. They give us in horsepowers. Of course, we should convert that to watts, like they told us there. And it tells us the time in hours and minutes. What time unit should we convert to? Seconds. We want to get in our base units. That's why we want to get the horsepower to watts. That's a joule per second. And then if we get our time in seconds, we'll be much happier. Notice the default units they're using. Megajoules. 10 to the 6 joules. Remember, you can always go in there and say, no, wait a minute, I calculated in joules, and just get rid of that M. And then you've got it in joules. Yeah, isn't that cool? Well, because I can set the problem so you have to enter the right units like I do on the test. And so those units are just default ones that go in there. So you can always edit those. And then they want to know how many bars given this. So let's figure out the amount of energy, and then we can convert that to candy bars. I'm sure you guys can do the conversion, because I've seen your chemistry grades. I know you're good at this. So the form I'm going to use here of this equation is not that one and not this one, the energy per time. All right, so, and they tell me the power. Oops. This one up. Okay, 0.3 horsepower and 1 horsepower, 746 watts. So I'm just over on the side. So my power, 0.3 horsepower times 743 watts per horsepower, right? Doing that little picket fence stuff that you guys all remember from chemistry, right? And then I want to know my energy, and I'm going to put that over my time, and I need to do that conversion of my time. I'm told my time is 2 hours and 49 minutes. So that's going to be a pain to convert. You know what I might do? I might take the shortcut. Go out here and put 2 hours, 49 minutes. Oops. Of course, it helps to be typed correctly. 49 min in seconds. And that is 10,140 seconds. Okay. So 10,140 seconds. Right? And I just solve for delta E. And that's going to end up, because I'm in seconds and watts, that's going to end up in joules, whatever it is. All right? And then the next part is just a conversion. That many joules, figure out how many candy bars is that many joules by doing that picket fence type stuff. All right? Questions on that one before we move on? Whoops, sorry. Get down and this stuff. All right, so we're doing number 13 next, and 13, we look at the Y, is forces, involving forces and other concepts. So we're going to need a force diagram in here, but we're also going to need some words. All right, so we have an airplane landing and begins to slow down as it moves along the runway. And they want to know what's the acceleration. All right. So this one's actually, I'm actually surprised. This one probably should have been just forces. But I'll follow the rubric here. So let's put in the forces first. And let's click down here, and I'm going to start off with net force causes the plane to accelerate for it to slow down. The acceleration and the velocity must be in the same or opposite direction. Opposite direction of each other. Yeah, that's probably why I said to do it this way, but alright, so now I need my diagram. Remember, stop me anytime if there's questions. So I'll get on a roll. So and then, now remember, you don't have to live up to my artistic ability, right? So here, I'm going to draw my plane. There we go. There's my plane. Hopefully I didn't do too many details. I'm saying its velocity is in that direction, which means its acceleration must be in that direction. and therefore the force due to braking is going to be in that direction. Now, there are a couple other forces on there that are useful to recognize. I don't really need them in this assignment, but of course I would have the weight of the plane down, and I'd have a normal force up on them, not the XB1, the 21.
So would you say that that force is sort of go down that way?
Yep. Right, that's, yeah. So which way do you want to call positive? That one, to the direction the velocity is going. So we're going to call this direction positive. Is that okay with everybody? Does it matter, really? As long you could pick either one, as long as you're consistent. All right? So it doesn't matter. That would be your diagram. Good? Let's scroll down. Now we need our valid physics equation. So I'm looking at force and inertia and acceleration. So I'm going to grab my friend Newton's second law, put that in here, and I only have that one force. That is the net force on it. And I'm expecting that and my acceleration to be in the same direction. So now let's see if I get the numbers in my head. Mass is 3.55 times 10 to the 5th kilograms, and the brake force is 440 times 10 to the 5th newtons. So that's my net force, 440 times 10 to the 5th newtons. Told me my mass was 5.5, was it? 3.55 times 10 to the 5th kilograms. And that's going to lead to my acceleration. This is negative, right? Because my force is pointing in the negative direction, which is going to give me a negative acceleration, which is great. That's what I expected. Because if the plane's moving positively, then it's going to be negative. My guess is in the answer they want the magnitude, so you get the value. But then now just solve for A. And if you don't get a negative value, you probably just made a slight math error, but you probably can put in the positive, and that'll be fine. So I think they asked for the magnitude of it, which would be positive. You can. Nice math look there, yeah. Yep. Because they asked for it in meters per second, right? So we don't have to worry about that. But yep, mathematically you can get rid of that times 10 to the 5th.
I have a question about one of the problems not on that. It's real.
All right, so on to number 16, which is you weigh yourself on terra firma, Earth, and you get this, and then your elevator's apparent weight is this. What measures apparent weight? Begins with an S. A scale. A scale measures weight. So what force is that scale actually measuring? Normal force. Not the force of gravity, right? Normal force. Scales always measure normal force. That's one of those factors you've got to put in your head someplace. All right? Scales measure normal force. So this actually this one should have been rather than just a diagram, this one should have probably had the Y in here. So I'm going to add it in there because that's such a key point. Scales measure normal force. This is 16. But all it asked for was the diagram. So here you are. There's the scale. Force of gravity will be down. normal force up. Notice how those are touching my object, right? Now they tell us the normal force, for mine at least, is less than the weight, in my case, right? So I have to think about, okay, that means if this normal force is less than my weight, which direction is my net force? Downwards for my case. So if my net force is downwards, which direction is my acceleration? Downwards. They're always in the same direction. Net force, acceleration, always in the same direction. That's another factoid to put in your mind. So, because my normal force is less than my gravitational force. If that wasn't true, if they were equal, I'd have no acceleration. And if they're opposite, if the normal force is greater than the weight, therefore my net force is upwards, I'd have an upwards acceleration. Alright? When I post the video, if you look at 15, I believe, from C block, you'll see that. Alright. Onward and upward. Let's see if I still have it. Yes. That's my equation. So now I have my net force over my mass equals my acceleration. Well, I need one more equation, actually. Because they tell me when I'm outside the elevator, they tell me what my weight is. And I'm going to need to use that. So from a couple units ago, we'll grab that one. So you weigh yourself on solid ground, your weight is this, and the elevator is this. What is the magnitude of the elevator's acceleration? Oh, and I just answered which direction, for me at least, right? So, if I start with Newton's second law, I have, which way do we want to call positive? Up or down? Up. Okay, we're going to call up positive. That means I have a positive normal force plus a negative force of gravity. So I'm filling in that top part over the mass, and that equals, and my acceleration I said was down, that equals a negative acceleration. Right, because the vectors, I have to put in the directionality. I know the normal force, I know the gravitational force, that's what my weight is on terra firma. I don't know my mass, I don't know my acceleration. That's why I needed to grab my definition of weight, so that I could find that mass. Now, I could solve that for this mass separately and put it in here, or if you want, you can just solve, you could put it in there and then solve for it. It will end up canceling out, but I think most high school math students would do it separately. So, so you take your f sub g, which they tell me is 530 newtons. Equals whatever the mass is, and then since I'm on Earth, 9.81 newtons per kilogram. And I left out my negative signs because I knew they were going to cancel out. And that will give me my mass, which then I can use over here, and then solve for my A. And I have this value, and I have this value. Happy days are here again. Right? And yeah, questions? number 12. Hot air balloon is ascending at a rate of it. What does ascending mean? Traveling upwards. Traveling upwards. And when a passenger drops the camera. All right, so right away I'm starting to think, oh, I got up, I got down. Which way do I want to call positive? Up? Okay. You guys are so boring, but okay, we'll call it positive. When the camera is 27 meters above the ground, when it's dropped, how much time does it take to reach the ground? And when it's dropped, what is its velocity just before it lands? Let upwards be the positive direction for this problem. All right. So, text. Purple. When the camera is dropped, it is not moving in the frame of reference of the balloon. Because that's what dropped means, right? Just released. Is it moving in the frame of reference of the Earth? Yes. In the frame of reference of the Earth, it is moving upwards with the velocity of the balloon. Once dropped, so it accelerates downwards due to the net force on it being its weight. It is in free fall. The further it falls, the longer it will take and the faster it will be moving at the bottom. Yay! Alright, so the tricky part here is that it's actually, when it's released, it's actually moving upwards. So if you were to think about the path that this follows, from the balloon, it looks like it just falls down, right? But from outside the balloon, so in the balloon we just see it falling down. Outside the balloon, it goes up, and then it falls down and hits the ground. Because it travels up with the balloon. Huh? So from outside the balloon, we see it travel up and then come back down. From inside the balloon, you just see it fall away. But we're interested from outside. That's why we had to make sure we realized that it was going to go up and then come back down. All right. On to here, and I'm not going to try to redraw that and mess myself up again. So we want to know how long, how many seconds it takes, and how fast it's moving at the bottom. So I'm looking for a relationship between its initial movement, its acceleration, and time and things. So right there. This, boom. And then I want to know how fast it's moving at the bottom. And I could actually use either one. I'm going to choose this one. Just because it has less scary math in it for you guys. So, yay. All right, so I actually need to do a little diagram here. Ground, balloon, camera. Okay, let's undo that one. Camera. Is that neat? I can draw a dotted line. Alright, so we need to establish which direction you want to call, oh, it said call up positive, right? So we're going to call up positive. Where do you want to say 0 is? I would either say let's pick the ground or pick the balloon. Ground? Okay. So we're going to say this is at a height of 0 meters. That means our balloon is at 27 meters. No, that's not that high. And then it's going to be moving upwards and things like that, right? But I think it's good to establish that because remember, all these, where you put the origin, all this is up to you. So, our big kinematics here, where we end up is where we start, how we're moving when we start, and how we're accelerating. All right? So, I end up at the ground, 0 meters. I started at positive 27 meters. My initial velocity was positive and upwards at 7.9 meters per second. I'm not bored. Stop. I gotta adjust this up. So positive 7.9 meters per second. I don't know how long it moved for. I'm dropping the delta just to make my life easier. Plus 1/2. Which direction is it accelerating in? The negative, down. Negative 9.81 meters per second, t squared. It looks scary, but just solve for t. You only have one variable. And it will be in seconds. Then you can go back, and for the second part, you're going to use V final equals V initial plus AT. V final is what you're looking for. V initial, you already know, positive 7.9 meters per second. A is going to be your negative 9.81 meters per second squared. And your T, you'll know. Do you expect V final to be positive or negative? The final velocity. The velocity just as it hits the ground. Negative. So you should get a negative answer for the second part. If you don't, check your sign. Because it doesn't mean your value's right. On these, it's really important that you get your signs right the whole way through. All right. I think you can do it from there, right? Okay. I'm gonna